We'll get this started now that we have all the technical stuff worked out. So we are going to start our meeting. It is just right around 6. And just a few announcements beforehand. So does everyone know that we're having a star party out at Lake Sylvia, March 21st and 22nd. The 21st will be for CAAS members and for the workers at the park if they decide to come out there. We're going to have a cookout. We don't know what we're cooking yet, but we'll cook out, have food for you, stay as long as you want. If you want to camp. If you want to, my wife and I are renting in one of the cabins. They're very nice. And so, they have 7 cabins, and they're very nice. Yep. The only thing they don't have is they don't have a kitchen. They have a refrigerator, but no kitchen. There's shower, toilet. It's very nice. Comfortable beds. But I bring my Coleman stove, and that's how I cook in there. And you're allowed to do that. Okay. On the night of the 22nd, that's the public star party. And that will be presentations in their main conference area, which is before you get to the peninsula where we're located. What we do need are telescope volunteers, and so we appreciate that. Bruce is running the show, so I'm sure he'll get another message out about telescope volunteers soon. That's this month, March 21st, March 22nd. It's on the calendar. All right. Second, in June 13th through 15th, our club is hosting the 2025 Mid-South Region of the Astronomical League Conference. And we're going to need some help there, people volunteering to help set some things up. It will be at UALR, and it begins on that Friday afternoon with registration. It will then move into the evening where we'll go out to Two Rivers Park, and there's going to be a food truck there. We'll have dinner. And then some people, if they want, can go up to the RRO to see whatever's there. I assume we'll have some telescopes set up if it's a clear night. The conference then begins at 8 a.m. the following morning and ends at noon on Sunday. Okay? So the good line of things. The website will go live early next week. You can register there, and there's going to be some good food. On Saturday night, we're having a banquet, and on Sunday and Saturday, lunch. Okay. So that's about, we got there. Yes, Aaron. 13, it's June 13th through the 15th. Okay. Yep. Okay. And we got a good programming. The keynote speaker is going to be Dr. William Hartkoff, an old classmate of mine from the University of Illinois Astronomy Department, and he's going to be talking about the Naval Observatory, its history, and the ongoing research. And I can't remember I think it's Linda Sykes, something like that. And she's the current director of the Voyager program, and she'll talk about the Voyager program itself, its history of discoveries, and what they have planned for the future. All right. So anyway, we've got a lot of things coming up. And the April meeting will be a Family and Friends Day. We'll start at 4 p.m. We'll have food, games, and things like that. And then hopefully, if the sky is clear, we'll have a star party. All right. That's the April meeting. I believe it's the 12th or the 13th. What is it? The 12th, April 12th. All right. So anybody have any questions? See, Rocky, you're going to still do your was it the stamp presentation of the history? Was it the space program or just the
history of the space race?
History of the space race in stamps.
Just using stamps to step through it.
There you go. All right. So we have 2 presentations tonight. I'm going to start off with mine, and then we'll move on to Ed. Yes, quick question from John Reed. Yes. Starts at 7, but the activities start at 4 because people are going to come out. Remember, like the last time we did Family and Friends? We're having Family and Friends Day, so they'll come. They'll We'll have tours of the place. We'll have several presentations. We'll then have dinner. You know, we cooked out last time. I made Italian sausage sandwiches and pulled pork. Somebody else should cook. We should have had that tonight, but no one. April 12th. Okay.
Hey, Michael,
Yes, sir.
I've got one thing. I've got an award.
Oh, okay. What's your award?
I got one today. I got the Solar Imaging Award, Solar Neighborhood Award.
All right.
I don't know if you can see it there. But anyway,
hey, listen, since you have that award, could you get the sun to fire up again and get us some more aurora?
it's by the solar neighborhood. It's the stars within 1 parsec or 33 light years. You know,
what's that, sir?
Stars close to us.
That's pretty cool.
I guess the sun is a star close to us.
So how many are within a parsec of us?
I think there's about 250 on the list or something like that.
Oh, there you go. Okay. All right, so I'm going to start with mine, and what I'm going to be talking about are some of the major contributions that the James Webb Telescope and the Hubble Telescope have made to astronomy. And I'm going to focus a little bit on something to do with star formation, which they helped do, and then move on to some conundrums that they've been addressing. And 2 recent papers coming out seems to have potentially solved it. So let's take a look. All right. Let's see, get this one to work. No, that's not working. I'm going to push the button there. Okay. So this image here basically presents and summarizes what's called the current model from the Big Bang to today. And it's called the current model for a good reason, because it changes. When something new is discovered, that becomes the current model. Now, if you see on the screen, you start from the Big Bang, and if you come up, you'll see this multicolored thing where it says neutral hydrogen forms, and it's 380,000 years after the Big Bang. And what that is the microwave background. And that is the energy and everything that was left over from the Big Bang after it spread out. And that gives you the background radiation and temperature, which is about 3 degrees Kelvin, not absolute zero. I'll talk more about that later and show you another picture. The problem is, everything that occurred before that, we can't see. There's no light. There's nothing that is left over. Everything had changed and moved into the positions there. There was mass, but there was little to no energy production. So we're going to have to look and have observations from the James Webb Telescope and everything like that for after 380,000 years. Everything else, which we can talk about another time, is theoretical physics, quantum mechanics, and the general theory of relativity. Okay? So we're going to focus on thereafter. So here's a closer look at it. And what you can see is that we get, you guys can't see the pointer, but you get the high ionized planet and this cosmic microwave background. After that, it says dark ages begin. That's because nothing's going on. No fusion, nothing. And then supposedly the first, yes. Okay, well, why don't you come up and ask it? Okay, John's got a question. There's tons of stuff going on, but we can't see it. Well, because that's what the plasma is, right? And we can't see it. No, I didn't say that. I said we can't observe it. That dark air ages, after that, after 380 things, there's not much activity. Right. It's before that, right? We can't see it or observe it. That's why they do computer models, which I'll talk about. All right. So, and then you get this idea that somewhere around 10 to 100 million years, we start seeing the first stars. And then galaxies, somewhere between 500 million to 1 billion years, they start forming. Okay? So that's the current model. It's much more complex than that. This is where we're going to focus. So, a very big thing happened in the 1960s. Two amateur astronomers were playing around with their radio telescope and they kept getting this, what they thought was interference. It turns out they discovered the cosmic microwave background. And you can see that it is not uniform. Thank God it's not. If it were uniform, we wouldn't be here. Something, and that's postulated to be dark matter or something like that, forced our current, what we call matter, to congregate in certain areas. And those are the hotter areas of the universe that we can see. And it's going to be like the yellow and the red that you see on this map. The blue is the coolest. What's important about this is if you plot on top of this all the super clusters of galaxies, they fall on the yellow and the red. The areas that are blank, not much. So what happened, and there's many theories about it, and I can't talk about it here, it takes too long, that forced us into this, and that is where the matter congregated and started gravitational collapses, which led to stars and galaxies. Okay? All right. So, the power of computer models. Because we can't observe anything prior to 380,000 years after the Big Bang, we have to use computer models, and we base it on our current models of physics. As I said, quantum mechanics, very important, and general theory of relativity. The events preceding the CMB are postulated on these laws, and either the old days, they used hand models, hand calculations to get some idea, but it really didn't become very clear and better until after computers started being able to models. So how good are the models? And that's an important question. And to give you a faith of that, I'm going to give you through this following thing. So, we could not see star formation prior to the Hubble telescope and the James Webb telescope. So they theorized what was going on. And this little scheme there shows a star forming, contraction, starting to spin, and taking its magnetic field, twisting it around, and saying, you can see there's the center area here, which is the accretion disk forming the star end, which would be forming the planets in the center, that little brown area. And there's the twisted, crazy protostars, and they predicted a jet of energy coming out. Okay, well, guess what? There you go. Off to the left in the gray diagram is what's called Herbig Haro object, HH. That's the model what predicted. Finally, all right. All right. So the gray diagram, you see the jet stream, you see this cup, and when they started with the WST and the Hubble telescope, you can see it. The dark area in the center is the accretion disk. These are the cups, and the energy coming out is not all the things that you see that are coming from the star. The star energy coming out in magnetic fields are ionizing and exciting the gas surrounding it, gas from which the star is formed. So it's a combination of some mass coming out from the star and some of it being ionized and elsewhere. And one of the things that they couldn't originally see was the star or the accretion disk. However, they had to twist and turn things around because they had to see through all the dust that's in the accretion disk, and they tuned the JWST, the James Webb Telescope. And here's one where there's two stars and it's forming this beautiful picture. That's one of the best I've ever seen. And there in the center, you see the bright thing. You can see the protostar and the accretion disk around it. Finally, they got it. You go to the NASA website, you'll see this picture, and you can blow it up in all its glory. Yes. It's the magnetic fields. You have the two magnetic poles, south and north magnetic poles, and the magnetic lines are twisted, which, remember, they're moving around. And what happens? A moving magnetic field creates an electric field and draws the material up and out. What did I do? Oh, no. What did I hit? Oh, shoot. All right. So how are we going to get this thing back for you guys to see? Hang on a second.
I'm seeing the NASA picture.
All right, Sean, I must have hit the keyboard or something, and then the TV here is not showing anything. How can I get it back?
I'm not seeing anything either.
You guys aren't seeing anything?
No.
Well, I am.
I am now. Now I am, yeah.
All right, but the people here are not seeing it. Any suggestions, Sean? I can see the cursor, but they can't see the PowerPoint.
Stop sharing on PowerPoint and reshare again. We may
What's
have
that?
Stop sharing on the PowerPoint and then reshare again. You may have to reshare on Zoom after you reshare on PowerPoint.
Well,
yeah,
again, we're still not seeing anything on the TV here.
Interesting. Well, we're seeing it on Zoom.
I know, but we're not seeing it here on the TV.
We're seeing the presenter's view, though. Did you, by chance, turn the TV off?
No, I didn't touch the TV. The TV is on.
If you don't get it, have everybody fire up their phones.
Yeah.
I don't know. The share button on the computer, each one different.
There you go.
Okay, it's back. All right.
There it is. Yeah.
All right. So now, do we see this in closer stars and nebula around our neighborhood? Well, here's the Orion Nebula, 1,300 light years from Earth. And when you look at the Hubble telescope, look there. Now, you said I'm on presenters mode now, so how do I change it to... Well, I'm not going to worry about it. So, when the Hubble telescope focused in, this is something you cannot see from any Earthbound telescope. You see, like over here in the top right corner, is a perfectly beautiful little example of what I just showed you earlier. And there's a couple like this, but then if you look, there's some distorted ones. And what's happening is all the huge, and there are a number of very huge stars, bright blue and white stars with high ultraviolet light output, are blowing apart all the accretion disks. So these stars will form, but they will not have planets. Okay, so that's what's happening. Okay. So you can see how both the James Webb Telescope and the Hubble Telescope have reached out, shown us how stars are forming, and that they agree with the theoretical models that were produced before we were able to make these observations. So computer models are pretty good at showing you what's going on as long as they're consistent with the current theories and laws of physics. Okay, so hopefully you believe that. We move forward. So there's been some things going on over the last couple of years. People think that the James Webb Telescope sent shockwaves to cosmology. For example, the first thing that was reported is they found massive, mysterious galaxies in the infant universe. Uh-oh. In other words, I showed you on that original diagram, galaxies weren't supposed to be forming until close to 1 billion years after the Big Bang. And they were going to be small galaxies. Well, here, 300 to 500 to 700 million years after the Big Bang, there's these big, massive, high-energy galaxies formed. Ruh-roh. What's going on? Okay. Another thing that confused people is they were starting to see the earliest supermassive black holes at the same time. Now, wait a minute. Supposedly, the black holes were coming from stars that had collapsed and then aggregated to make the massive black holes. How could they be there? The quasars, back at around 300 to 500 million years after the Big Bang. And people were all trying to talk this out, trying to solve it with things like how dark matter interactions or how dark energy, or, oh my God, we're really messed up and the models are not good. Well, that's not true. So, resolution. More recent and concise measurements that have shown that there is more intergalactic dust and gas than expected in the universe. The James Webb was able to show this by changes and fluctuations in the infrared region of the spectrum and realized it's dust. So we thought these galaxies were younger because their redshift was greater. It wasn't. They were redder and looked older because of the dust. When you correct for the dust, and that's what they're able to do with the scintillation models. Go ahead. They're not immune to dust. No. But they cause the absorption of certain lines, and it makes it look like they have shifted. And that's what they did. So, oopies. I do. I'll send you the papers if you want. So therefore, these early galaxies were formed later in time. So therefore, the supermassive black holes were formed later in time. So now we're back. But why are they so big? Based on so much energy. So they looked at the light coming from them and said, oh, this is how massive they are because this is the star production. Well, it turns out it's likely that these supermassive black holes formed from aggregation of black holes that occurred right after the Big Bang. They were smaller and they started to aggregate. And now it's postulated that that was necessary for most galaxies to form because it held the matter together and brought the matter together that would form our galaxies and then all the stars that came about. Okay? And that 50 to 80% of the energy coming from these early galaxies is from energy and light produced by gas being pulled into the supermassive black holes into its accretion disk. And these early galaxies, more of the light is coming out not from stars, but from the accretion disk of the supermassive black holes. Wild, huh? All right. So, well, we'll wait to the end. We'll go there. So the first mass determinations of these galaxies were grossly overestimated. Regardless of what's going on here in the exact numbers, we are seeing new things. Galaxies have formed and stars have formed earlier than expected, but not too much earlier, maybe 10 to 15% earlier. So that's within experimental error and error of the computer models. Okay. So, have anyone heard about the Hubble tension? So it's called a cosmic calamity. Well, again, since 1929, we've known that Edwin Hubble, that galaxies are moving away from us. They're redshifted, except for a few. The Andromeda galaxy is coming right at us. So it's blue shifted. But everybody else is moving away. Maybe because they're seeing a big collision coming, they're saying, we don't want any part of that one. Who knows? All right. But it's been surprisingly difficult to pin down the actual rate of shift, the actual number for the Hubble constant. All right. So one hope is that JWST, the James Webb Space Telescope, could pin this down better because it could see through all the gas and dust that was absorbing a lot of things, messing with redshift lines and things, and maybe get us there. Pretty cool, huh? Well, things got confusing. So how do you measure the Hubble constant? One method is looking at that big microwave background, the cosmic microwave background, looking how it is shifted and looking at its distribution. It's a computer model that's got to go through, and it came up with a value of 67.4 kilometers per second per megaparsec. Okay. A second method is to measure expansion of galaxies in our local neighborhood directly using stars whose brightnesses are known, Cepheid variables, type 1 supernovae, and a bunch of other things. There's a number of stars that they're called the candles that we can use and get landmarks. The nice thing is the James Webb Telescope gives us a better opportunity to make more precise measurements than the Hubble could. Okay? So there's a new study by Friedman et al. From the University of Chicago. And what they did is in 10 fairly distant galaxies, ones that could not be measured using the Hubble telescope, they used 3 different methods to determine their distance and their rate of expansion away from us. They used the Cepheid variables. It's this different thing to explain. It's called the tip of the red giant branch, knowing that certain stars could only get so bright. And when they do that and they show the characteristics of the red giant, which is very easy to see on the spectral lines because of the different shell fusion levels, they can say this is maximum brightness and we know what it is. And then they can measure the intrinsic brightness of carbon stars, which are fairly common, but you couldn't see them in other galaxies because they're red and not very bright. The Webb telescope can see them. All right. When they did this, this is just an example to show you what I'm talking about. If you see here, these are the areas of the same areas with the James Webb telescope on the left. Look at the resolution. And that's what the Hubble was showing. It was so pixelated, they were trying to focus in on the individual pixel to get the measurement, and they couldn't do it. Now they can. All right. So Friedman's study produced a constant of 70 kilometers per second per megaparsec, which is in the range of the error, within the margin of the error of 67.4 that was produced from the cosmic microwave background, okay? Wow. Wait a second. The other studies that were done using the Hubble and other telescopes came up with 74.5, but they could not see and make the measurements that the Webb telescope could make. So now we have these studies coming out showing that the cosmic wave background measurement, which everyone considered the gold standard, is coming up with the same number as these other methods using things like type 1 supernovae and the Cepheid variables. So what does that mean? Well, it seems to suggest that the rate of expansion of our universe has not increased. It is not going faster. It has remained constant. If that's the case, they were saying that there's dark energy, which was postulated to be pushing it all out. Maybe there's no dark energy. Whoops. And that's an interesting result. Obviously, there are astronomers contesting this. All right? And this is a really interesting thing, and this is what's causing a lot of discussion. So look for this in the astronomy magazines and in the news from NASA. It's very interesting. This study has no effect on the theories and measurements regarding dark matter, only dark energy. Because dark energy was associated with, postulated to be associated with increasing expansion, and it doesn't look like there's any increasing expansion. Really interesting. Wow. So obviously astronomy and cosmology are changing, and WST, James Webb Space Telescope, and the Hubble Telescope are showing us new things every month now. Because if you go back to August, before this paper came out, everyone was, heavy into dark energy as the culprit. So I gave you 2 websites here. I'll mail those out if anyone's interested. And you can go to these websites. Go to the NASA websites. See what's being posted all the time. It's fascinating. Beautiful pictures if that's all you want. But they also keep you updated with the latest theories and the latest papers coming out. Okay, thank you very much. Any questions? Why don't you come on up here and do that, Aaron?
So, if you're interested in learning more about this, I've been following an astronomer, like professional astronomer named Dr. Becky. That's what she goes by on the internet. And she's covered the same Friedman et al. Papers and makes some really great videos as like night sky news videos to tell you what's coming up the next month too. So it's pretty nice. And yeah, she if I remember correctly, studies the formation of black holes. So this is something that she's really interested in and talks about a lot on her YouTube channel. Just going to add that.
John has a question. Dr. Becky, I've listened to some of her stuff. She does a very good job of bringing it down to layman's terms.
Yeah. All right. I'm trying to remember all my questions. The first one dealt with your black hole stuff. You said there's more gas and all this, and therefore we hit bigger black holes more quickly. Okay, but that's not my question.
People thought that dark matter might be these nascent tiny black holes. Oh.
If the black holes form faster because there's more material, how come right after the Big Bang it didn't all just suck into a black hole because everything was more dense than anything?
You have to look at it the way why does a star not collapse all the way down? Because you have, as it starts to fuse, it produces energy that comes up. So there was enough nascent background energy to push out, and that's why the black holes were tiny at first, and to push them out. And then once with the dark matter, whatever, started to see forth the condensations that you saw in the cosmic microwave background, that's when the collapses, gravity took over, bringing things together. Because the universe was cooling down, right? As it expanded. It blew out very fast. You have to remember, supposedly it grew out more than 50% of its current size within the first 3 microseconds. That's called the inflationary period. It was short. Okay.
I've got a question.
Sure. Go ahead. Go ahead, Carl.
Going back to your first slide, I was confused where it says fusion stops.
That they were talking not about fusion of nuclei, but the fusion of the primary particles into atoms and molecules. So that's not a good word to use, the fusion. That was fusion of the fundamental particles to form atoms.
Thanks.
You're welcome. Anybody else have a question or a comment? Okay. All right. Well, our next speaker is going to be Ed Swaim.
All right, Rocky asked me to do a constellation of the month, and looked around, and Orion is up in front of my house at night, and I can see Lepus a little bit. So I thought, I'll do that one. And John Reed just said it was kind of a sad little constellation. If you look at look at Bayer's illustration, I think the Hare that he drew is sad looking too. One of the things I did was look up the difference between a rabbit and a hare. And apparently Hares are bigger. They got bigger ears, bigger legs, and they live above ground, and their babies are born with their eyes open and they can move around. And rabbits, their babies they have their eyes closed and they can't move around or anything. And they're born in burrows underground. So hares must have been of more interest as an animal to hunt. I have no idea about jackalopes, but I think there's a jackalope on my next slide. I'll show you. All right. So that's Bear's illustration, and a lot of his designations and names for stars are still with us now. So where is it? If you, again, look up at Orion about this time of year, Lepus is underneath Orion, and usually just grazing whatever your horizon is. If it's houses or treetops, then you can see usually a kind of a 4-star pattern, and that's what I can see from town. It's about 4 stars that make that up. And over to the left of that, I'm not going to try to do east, west, south, and north right now, but is Sirius, and of course Canis Major, right there, the big dog that in this illustration appears to be chasing the hare. And then you've got Rhinoceros, which is not a jackalope, I guess, but another animal where somebody glued a horn on its head. I don't know. They got it as a unicorn on this one.
Yes, they did. Stronger communication with the agent. I thought it was. Oh, well. Anyway, go on.
All right, so Lepus is there, and supposedly either Orion's hunting the hare or his dogs are chasing the hare, and there are all kinds of other ways to look at it. But it's been a constellation for a long time. Ptolemy included it in his list of 48 constellations back in the 2nd century, and so it's apparently been significant enough to caught his attention back then. Naked eye, I can see 4 stars in it, and sometimes I can see some of that pattern that makes up the little ears if it gets binoculars out. But you've got the brightest star is at the corner of this little square, Arneb. It's Alpha Leporis. It's a magnitude 2.6. You've got Gamma, which also has the name Nihal, and it's a magnitude 3.6. It's down here. But that rectangle is really what you see, especially when you have such other bright stars right around it as Sirius and Rigel, other stars in Orion. So it's kind of dim and hiding down there. And it doesn't have very many other objects in it or near it, but it has a few. And a couple of the references that I looked at when I was looking at these, one is William Tyler Olcott's Field Book of the Stars. It was updated by the Mayalls, who, I bet, John, you've got a Mayall book on sundials, but I don't know. You make a lot of sundials. But they wrote some sundial books, I think, in the 50s and 60s. But William Tyler Olcott founded the American Association of Variable Star Observers and wrote this little book, and it has great illustrations in it. That are very simple. And his book was written in the early 20th century, so you weren't dealing with giant telescopes or sophisticated telescopes. Your main way to look at the stars is to go outside, and you might have what he called field glasses or a small telescope. So he goes through all those things in this book. It's one of those things, if I had it to do over again, I would have just bought one thing like this and gone through the whole book instead of try to pick all these different references and things like that. You have a whole lot more fun with this I think, than trying to figure it all out at once. Yeah. Also, Phil Harrington wrote a book called Touring the Universe Through Binoculars. It doesn't have any illustrations in it. Somebody liked his book and they wrote a little computer program that's just a few megabytes, but it's a whole star chart that has all the stuff in it. And you can download it and run it. And it kind of looks primitive compared to something like Sky Safari, but it's practical and shows you where to look for the items in the book. So that's another place for a small, kind of out of the way constellation like this to just get some good objects to look at, good descriptions, and just go enjoy it. So if naked eye, you might get some more of these stars if it's extremely dark, but primarily you're going to get those 4 that outline that main part of the rabbit. There is something that's really fun to look at that's near Lepus. It's Hind's Crimson Star. How many of y'all have looked at it? Do you? Tell your story.
All right. So Hind's Crimson Star. I've always heard of it. I've never bothered to hunt it down. Maybe because I forget about Port Lepus. But Port Lepus does have this. And I was photographing Orion a while back. You probably saw some of my Orion pictures. And I had one that went way down and covered, because I'm using a wide angle lens, it covered most of it. So I was looking at this image and I'm thinking, oh, I need to look up where Hind's Crimson Star is to see if it shows up. So I'm looking like in a chart kind of like that. And it's not very bright apparently. But on my image, there was this little red dot right where it was supposed to be. So I guess I got it. Just a little red dot.
Well, I had to change the magnitude of stars that would show up on Sky Safari to get it to show up on this chart. But it's marked over here with the little cross hatches, and it is so red that it almost doesn't look like a star. It looks like something's wrong if you're looking at it. Yeah. And it's been described as a drop of blood. I mean, it is so deep red out there, and it really kind of startles you when you see it if you are looking for it. But it was discovered in 1845 by a man named Hind. So I don't know if he named it, but they called it Hind's Crimson Star. It's a carbon star, and it does have a long period variability to it. Yeah. It's real fun to look at. Yeah, Rocky?
It's probably a lot redder when it's at its minimum magnitude, lower magnitude.
Cool.
Like it goes from 5.5 when it's max to 11.7 when it's minimum. And normally those kind of stars get redder when they're at their lower magnitude.
It's harder to see, too.
Yeah, but it's fun to look at one that looks like you're saying blood red on a dark background.
Yeah. Oh, yeah. So there are a few other objects around Lepus, and these are mentioned by both these authors because you can see them without really sophisticated equipment. One of them is M79, which is one of the Messier objects. It's kind of it's way down toward the horizon. It is a globular cluster that may be from somewhere else. It may be not associated with our galaxy, but might have come from another one on its way past us or something along those lines. That's as close as I get to cosmology. But it's got a real bright core to it. And then Gamma Leporis, which is over here, one of the dimmer ones there. It's a double star with a yellow magnitude 3 primary and an orange magnitude 6. So it's a nice little double. And then NGC 2017, it's kind of in the middle of the rabbit, and it's a little. This picture's from Wikipedia of NGC 2017. It's a little star cluster. That means one of the Herschels saw it back in the late 1700s, early 1800s. So it was visible in a telescope. Bigger than that one, but not much. Here's another illustration. The rabbit looks a little happier, but the dog's a little closer to him in that diagram. Maybe. All right, that's my presentation.
All right, thank you very much, Ed. Everybody to get out there and look at research. All right, before we close out the meeting, does anybody have any new business they want to discuss or announcements to make?
Michael?
Yeah.
How many people do we have at the RRO tonight?
Yeah, there's all 6 of us.
Cool. And then 10 on the internet.
Here you go. We took down the names of the people here, so that's available for record. Anybody else? I want to give a special thanks to Sean, who was able to talk me through getting this thing set up. It's not difficult, but when you don't know what you're doing, that's pretty tough. So I really would like to see us help Sean to put something into a form of not just writing, but also maybe with some illustrated pictures so we know what we're looking for, so that any one of us can set this up. When you look backtrack yourself, it's beautiful. And I think it's simpler than what was set up earlier, but as they always say, you got to know what you're doing. All right, anybody else with anything?
Should be a lunar eclipse on Thursday night after midnight, 1 o'clock or
Correct.
something.
We have a lunar eclipse coming up. I believe it starts earlier than that. It reaches, I believe, the peak at 11 and ends like 4 in the morning or something like that, 3 or 4.
I threw a link to time and date in there on the chat.
Okay, well, because of daylight savings times, it might be 2. I would look, if you wanted to get information about it, there's the Astronomy magazine and the Sky and Telescope websites, which you can enter without having a subscription, and they list all that information. Timeanddate.com as well. Anyone else? I do want to mention, and maybe we can have a star party there sometime, is last couple of weekends ago, Mike Hewitt, Ken McLeod, Jim Dixon, and Sean and I went down to an area near Kirby, Arkansas, and Mike Hewitt has a cabin down there, which makes it look like a shack from the outside, but it's a beautiful home inside. It's crazy. And we went to his neighbor farmer. He let us out there. It's somewhere between Bortle 1 and Bortle 2. It's not Bortle 2. It's not Bortle 1. It's like Bortle 1.5, something like that. It was amazing. Southwest a little. Yeah. And it, as I mentioned to some people, it was, I took a couple of pictures, but I mostly spent the time observing visually because I could see the nebula around the Pleiades through my eyepiece. I could see spiral arms in M81. I've never had anything that dark. It was truly exciting. So maybe we can arrange to do a star party for the people down there. That would be great. I think it would be wonderful. All right. Any other new business or old business? Anyone here at the RRO? No. Anyone on Zoom? No.
Might remind everybody that we'll have Kids Space Art the 12th of April.
Okay, that's always one of the activities, and I'm hoping that the Sanders will also do their rockets and other things, and we'll have games and activities. All right. Well, thank you all for joining the meeting, and hopefully we'll see you soon.